to the next presentation by Lennart.
All right.
Welcome, Lennart.
Let's see if I can share the right window here. There.
Everything is set up.
Yes, all right. So I'm going to talk about this library that I wrote called Orthotope. I think it's pronounced Orthotope. I don't know. I've never heard anyone say that. I just had to pick a name. So let's get to that slide. According to Wikipedia, an orthotope is like a rectangle, but generalized into n dimensions. So this is because this is arrays that can be n-dimensional, and all the good names were taken, like array and tensor and things like that. So I looked for something with a similar meaning, and so I found orthotope, which I'd never heard of before. It's a terrible name because I can't even remember it myself, but there it is. So so first I should say, if anyone has any questions, please try to interrupt me by posting them in the YouTube chat or something. I'm going to try and keep an eye on it. So first, I should say something about APL, because this is inspired by APL. So APL stands for A Programming Language. So that's a nice, simple name. It's a mostly array-based language. It was designed in the 1960s by Ken Iverson. And I'd say it is way ahead of its time because it's very much a functional language and a mostly sort of immutable data types. It does have variables, but the arrays, you don't really update them, you just create new ones. And if you've heard of APL, you've probably heard of it because it's supposed to be very cryptic, and I'd have to agree with that. So this little program that I've included there computes prime numbers from 1 to R. And yeah, it's fun, but hopefully the Haskell code is not going to be quite as cryptic. I think one reason APL never became popular was that you needed to have a special keyboard to be able to use it, because you can see there are lots of weird symbols in it. And so who has a special keyboard? I don't know. IBM, I guess, because Ken Iverson worked for IBM. I've actually worked on a small machine that IBM made that had a special keyboard, but otherwise it's unusual to see. All right, so Orthotope is, as I said, a Haskell library, and mostly it contains operations that I call structural. So it sort of changes the shape of the array without actually computing anything. So I made this library when I worked at Google, and so it's sort of geared towards the stuff that you want to do when you do machine learning things. So the way you set up neural nets, there's usually a lot of array manipulations, multidimensional arrays. And a lot of these structural operations are, maybe surprisingly, constant time. They don't actually do anything to the underlying storage. They just whistle things around in the sort of the array descriptor. I will show some examples of this later on. So I'm going to show you a bunch of examples. That's basically what this talk is going to be. And then I have a few more slides. And thanks to Google for making this open source. I no longer work for Google. I work for Epic Games now, but they have nothing to do with this whatsoever. Epic Games is hiring, by the way, but we're mostly hiring C++ programmers, so it might not be something that this crowd is interested in. So first, I'm going to display arrays in the same way as APL does. So here's a sample array. Has rank 2, as it's called. It has 2 dimensions. It's 2 by 3. So 3 is sort of the innermost dimension. It goes horizontally, and then you have a new line and you have the next dimension. So the shape is 2, 3. The rank is 2. The rank is simply the length of the shape. And the size is the number of elements. And so 3, 2 array. So an example of something with shape 3, 1, 2, 3. You can't really distinguish if it has more outer dimensions that have size 1 because they print exactly the same way. But they have different types, so it's important to know if you have something of shape 3 or shape 1, 3. 3, 1, on the other hand, looks different. And as I said, you can have, well, as many dimensions as you like. So here is a 2 by 2 by 3. So first there are, the innermost is 3, and then there's 2, and then there are 2 groups of those 2. Here is another one, 2 by 2 by 1 by 3, as rank 4, another 12 elements. If you see a single thing like a 1, that could be, well, it could have many dimensions. So one is that it could be a 1-dimensional array that has rank 1 and still has size 1. But you could also have arrays that has a shape with no dimensions. That's allowed, and they are often called scalars. So that's sort of the degenerate case of an array. And there is one value in this. You might think that's weird. There are no indices, so how could there be one value in it? But it's the only thing that makes sense. So if you look at the size is always the product of all the numbers in the shape. And so if you take the product of the empty list in Haskell, you're going to get 1. So it makes sense that there is one element in that array. All right, so this library comes in a number of variations depending on how strongly typed you want the API to be. So I'm going to say more about that. I'm going to show the version that is the most strongly typed, where the shape is part of the type. And to do that, you need to turn on a bunch of Haskell extensions so that you can have numerical things in your types, and you can have lists in your types. So here are some sample types. So an array, a 2 by 3 array of integers has this type, array 2, 3 int. 6-element array, which often called a vector of floats, would be array 6 float. And then here is a 4 by 4 by 4 by 4 array of booleans. So it's nothing strange about this, except that you can have these numeric types. So if you haven't seen that stuff in Haskell, this might look mysterious, but you need to turn on some extensions like data kinds, and then you can have these kind of types. And if you have a proper dependently typed language, then these would be sort of the same kind of numbers as the one you compute with, whereas in Haskell, these numbers are type level numbers, which are very different from the object level numbers. All right, so now I'm going to switch to my terminal window instead. So instead of showing you slides, I can type in some window. There is, that seems to be working. Okay, so let's have some simple examples. I hope this is large enough so people can read it. Let's make an array. The easiest way to make an array, or one easy way, is to say from list, where you can give it a bunch of numbers. And well, from list has no idea what the shape of the array should be. So you really need to put a type on it if you're going to get anything out of it. Otherwise you get some error message that it can't figure out what it's going to be. So the PP is just a function I have for pretty printing things. So pretty printing A gives you this 1, 2, 3, 4, 5, 6. If you just look at A without pretty printing, it kind of shows you how it was built. If you type this back in, you will get the same array. So if we look at the type of from list, you can see that it takes a list of elements and gives you an array back. And the first argument to the array type constructor has to be a shape. Okay, so it's kind of tedious to give the type this way all the time. So instead, you could say instead A equals from list, and you have to have another extension on Haskell turned on where you can actually give it type arguments. So the shape is the first type variable in the, if you look at the quantified type for from list. So you can give that explicitly and then say 1 through, well, let's 1 through 6. And now if we look at that, we get exactly the same array. And this is the way I will usually write things with explicit type application. You have to use that a lot if you use this library and have the sort of the strongly typed version of it. And if we look at the shape, well, it's 2 by 3 as expected. The rank is 2. The rank, remember, is the number of dimensions. So it's the length of the shape. So that's 2. And size of A is the number of elements, which is 6. Another nice way of making arrays it comes from APL. It's this function called iota because it was written in APL with the Greek letter iota. And it gives you all the numbers from 0 up to this 1 minus 1. All right. Any questions? No, I'm surprised. I hope the question stuff is working. Well, so what can we do with an array? Well, so something typical we can do with an array is to index into it. So let's do that. There's a function called index. We should pretty print the result. So you give it a single index, and that means you will index into the outermost dimension of it. And the outermost dimension is the sort of 1, 2, 3, or 4, 5, 6. So now I picked 1, 2, 3. Oh, sorry, I picked 4, 5, 6. If I index by 0, I get 1, 2, 3. And then I can, of course, since that's an array, I can index into that again. And then I get 4. And if we look at what is the type of this when I've indexed twice, well, it's still an array, but it's one of these scalars. So it's an array with no dimensions. So if we just showed this thing, it would show like that. But if we pretty print it, it looks nice. If you absolutely want to leave the wonderful world of arrays and get back to normal numbers, there is a function called unscalar that takes a scalar thing and gives you back the actual number in it, or whatever it is. It doesn't have to be a number. And if we look at the type of unscalar, we can see that, yes, it only takes one of these zero-dimensional arrays and gives you back the A. So yes, indexing, not very exciting. Next one is not going to be very exciting either. So here's our A. There is a transpose function. And if you're doing any matrix algebra, you think of transpose as just flipping the two axes. But these arrays can have an arbitrary number of dimensions. So there is no meaningful transpose that doesn't also need to know how to transpose it. So we need to say, okay, this has two axes. How do we want these two axes to be permuted? So if we say the zeroth dimension should go map to 1 and the next one should map to 0. So this will be ordinary transpose. If we do the permutation is just 0, 1, then nothing happens. So for just two-dimensional arrays, this is sort of a bit nonsensical, but if you have multidimensional arrays, you need to give this permutation. Then you might wonder what would happen if you, well, I don't know, make a mistake here. Then you get a horrible error message that says that, well, you used transpose in some weird way. There is no dimension number with index 2. You have the 0 and 1. I see someone ask me here if I considered naming it an array library. Yes, I did actually consider naming it array. But I don't, yeah, that name is sort of means so many things in Haskell already. So I wanted to have a more unique name, but it might have been a better idea. All right, let's just do another little transpose here. So let's make a different B. Make a three-dimensional array here. Well, I could just make a mistake here and so you can see what happens. So from list is of course impossible to have any strong typing of because you don't know what the length of the list is. So you will just get the runtime exception saying size mismatch. But if we do the correct ones, so here is the array. So there are two blocks. That's the outermost one. Then there are 3 rows in each of those blocks, and each of those has 4 items. So now you could, for instance, well, there are many ways you could transpose this. I don't know, 2, 1, 0. Which, well, I won't go through looking at this, but I mean, you can see it has the innermost dimension is now the one that was outermost before. So 1 and 13, and then 2 and 14, and so on. So now you can see why you really need to give it some kind of permutation here rather than just saying transpose. You might wonder what the type of transpose is. You don't really want to see it. It's some bizarro type using all kinds of type level programming features of Haskell. But transpose will check that what you're giving it is right, otherwise you'll get a type error. All right, so here we have A again. Another thing you might do with your arrays is to what is called a reshape, which is written by the Greek character rho in APL. So I could reshape this into a 3x2 array. So this doesn't do the same as transpose. This just says keep the elements in exactly the same order as you had before, just interpret them as being a 3x2 array instead. So it's still 1, 2, 3, 4, 5, 6. Or you might say, oh, give me, oops, Haskell quirk, 6-element array, or you can have a 6x1, and so on. And here's a somewhat nice thing about type inference. So I'm going to reshape iota into a 3x3x3. If you remember when I showed iota before, I gave it a type level argument saying how many things I wanted it to produce. So I need 27 things here, 3x3x3. But I don't have to say that because the type checker can figure out that, yeah, 3 times 3 times 3 is 27. So it must be iota 27 here for it to make sense. So sometimes you don't have to give these type level arguments because the type checker can't figure out what they're supposed to be. What's the type of reshape? Well, that almost makes sense. Takes an array of some shape into an array of some other shapes. They have to be shapes. And here it's expanded something. The size of the shape and the size of shape prime should be the same. That's what that's saying. All right, let's make a different B here. So it's a 2x3x1. So the innermost dimension is 1. So there's only one element per row here. So another fairly common thing you want to do is that you want to sort of duplicate some elements along some axis. So there is an operation called stretch. And you tell it how you want to stretch it. And so you can only stretch dimensions that are of size 1. So this says 2, 3, 1, and I want to stretch that to 2, 3, 5, which means you'll get 5 elements along each of these instead of 1. Okay, there was a number of boring sort of structural operations. You can do other things. Like you can add them, and you can add one. You can have other numbers than 1, 2, 3, 4, 5, 6 in your array. It's just that I've used that in all the examples. Let's make another little thing here. Okay, so this is 2 elements, 100 and 1000. So now I want to add these two C to A, but I want to sort of replicate the 100 along the first, the innermost dimension, and 1000 along the other dimension. So there's an operation called broadcast that can do these kind of things. That did not work. C. So broadcast again has some type level argument here that says, okay, the dimensions that C has, where are they going to end up when we broadcast? So broadcasts increases the number of dimensions you have, because it needs to be a 2 by 3 after you've done the broadcast. And this is saying, okay, the dimension that I have here, that should end up as dimension 0. So you can do all these kind of broadcasting things if you have, say, a vector and an array, and you need to add them. They could be slightly fiddly. So some APL does a lot of these broadcasts automatically, but it always, some of them work without writing anything. So this one I think would have done the right thing in APL if you just say A plus C. But there are often choices which dimension you want to broadcast. So one of them will be the default one, and that works easily. And if you don't want that one, then you have to write something more complicated. So I decided you have to write a complicated thing all the time in Haskell. All right, so let's see. Okay, so let's do another. Look at A, just to remember what that looks like. So there is something that is like the fold operation in Haskell, kind of like fold. APL calls it reduce, so I call it that too. So it takes a function, what to do between all the elements and how to start it, and then some array. And so this added up all the element 1, 2, 3, 4, 5, 6. If you add those, you get 21. But it might not be exactly what you thought, because it didn't return a scalar. It didn't return an int, or it returns a new array, a scalar array that has 21 in it. So if we look at the type of reduce, it has an unusually simple type. Takes this element-wise thing and how to start, and an array of any shape, and it will do this operation between all the elements and give you an array that has the result in it. So you might wonder, why do you want the result to be an array? Well, we'll see here in just a second how this can be useful. So let me first define this function, so I don't have to type so much. So sum stat function. So this did reduction of the whole array. What if I didn't want that? What if I wanted to only sum the elements of every row? So I want to add up 1, 2, and 3 and get 6, and I want to add up 4, 5, and 6 and get 15. Well, like APL, there is something called reranking. So what does this do? Well, it says take the array A, and this number here, 1, says go one level into it and then apply sum to all those subarrays. So one level in, you have 1, 2, 3, and you have 4, 5, 6. It will apply sum to those, and that sum sort of replaces the things that you added up. And so you're still left with one dimension because you went one dimension in, so the outermost is still there, which then has 6 and 15 in it. Okay, so that's fair enough. What if I had wanted to add up columns instead of rows? I mean, rows, that's fine, but columns is also good. Well, the way you do it in this library is that, well, you have to first make them into the rows then, so you can use the transpose. So first you flip the two axes of A, and then you go one level into that, and you add those, and then you get 1 plus 4, 2 plus 7, 3 plus 6. And do I have my B here still? No, it's a boring B. B equals from list. And you can, of course, go more than one level down when you do your re-ranking. So this says, look 2 levels into the array B and then apply sum to those subarrays. So it will add up 1, 2, 3, 4, and you get 10, and 5, 6, 7, 8, you get 26, and so on. So given re-ranking and transposition, you can kind of take your, if you have some function that goes from arrays to arrays, you can make it perform this operation on any sort of sub array or sort of any of the axes that you want. You need to transpose to get the axis in the right place, and then you need to re-rank to get it to apply to the correct subpart of the array. So I'm going to do a matrix multiply, but just to remind you what that looks like, I'm going to need to share the other screen again because I have a slide. So if you don't remember matrix multiply, let me give you a little reminder. So you have 2 matrices. So I have my favorite examples here: 1, 2, 3, 4, 5. Oh, 5, 5. Well, it's oops, that's just 5, 6. It should have said. Why change a winning strategy? So to produce this element in the output, you take sort of the first row of this matrix, first column of the second one, and you multiply them element-wise together and add it up. So that's the dot product of the 2. So 1 times 11, 2 times 13, 3 times 15, you get 82. To get the next element, you take the first row, you take the second column, and you do the same thing, and you get 88, and so on. So let's see how we can do that. And with the operations that we have. So let me switch back to terminal again. Right. So let me make the same B as we had. So A, we have the same old one, but let me make a B that is the same as I showed on that slide. From list, so it needs to be a 3x2, and it had 11 through 16 in it. So that's the one we had. And so one of the first things we need to do is to transpose this one. So so that's, you could probably guess what that looked like. So let me show you the idea of this. So we're going to broadcast both A and B, but in slightly different way, so they can be combined to achieve all these products that we need. So let me give this a name, AS. We're going to broadcast A, and since I need to give it lots of types here, since I'm doing it, the type checker doesn't know how I'm going to use it, so it needs some help. If you write it in one big function, it's much less types in here. So now we broadcast this dimension, so we get blocks of 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6, 4, 5, 6. And then we're going to do a similar thing with the transposed B. So BS will be broadcast. But now we're broadcasting slightly differently. And this also needs to be an array, 2 by 2 by 3. So this has been broadcast. This doesn't look right. Oops, AS was wrong. Sorry. There's AS, as it should be, and BS. So you can see that AS has broadcast things so that there are 2 duplicates of this here, whereas this has this block duplicated over here. So if we now just take these 2 and multiply them together, then we get all these products of elements that if we sum them now, if we sum every row, those will be the 4 elements that is the result of the matrix multiply. So let's do that. And there is the result. And there is, of course, no looping or anything in sight. We just take the matrix and reshape them in different ways and combine them with sort of array-sized operations and get the result. Okay, I'm going to switch back to the slides again. So if you combine these things together that I just typed into a function, called it MM here, it will have this type. And so you can see, if you ignore all the constraints here, you see that it takes an array of m times n and an array of n times o and gives you an array of m times o. So the inner sort of the second dimension here and the first here, is the one we're summing across. So that one disappears. And this is the same as I did before, but just with little less type annotations on it. So AS, you broadcast the A, BS, broadcast the transpose, rerank, adding up the elements, and that's it. Now, if you actually want to do matrix multiply, you shouldn't do this, because the Orthotope library also comes with an interface to the H matrix Haskell library, which uses BLAS and LAPACK, which is written in, well, depending on what platform you run on, it might be written in Fortran, it might be written in C, but it's very fast matrix multiply. So this was more to illustrate how you can do things in Orthotope. So a few words about implementation. So all these operations that I did, like transposing and stretching and broadcasting and so on, they are not expensive. In fact, they are all constant time operations, because they never touch the actual elements. And this is an idea that dates back to the 60s too. The IBM called them dope vectors. So this is, an array has some piece of storage and some kind of descriptor of what the array is, and that's what's called a dope vector. And if you want to be mathematical about it, so any affine transformation on the index space can be done in this and done in constant time. And I've written the complexity. So transposing, windowing for if you want to do convolutions, slicing, reversing, indexing, striding where you skip elements, they're all constant time. Reshape, re-rank, they might be constant time. It depends a bit on what you've done before. And of course, the thing that has to do with sort of computation and touch all the elements, you have no choice but having them be linear time, or worse than linear if you're doing something complicated. So before I talk a little bit of implementation, I'm just going to mention all the variations that are of this library, unfortunately. So there are 3 levels of types. So I've shown you the ones that's called shaped, where the shape of the array is actually part of the type. So an array 3,2 int is a 3x2 array. Slightly less strongly typed, they're called the ranked. Then it's only the rank, so you only know the number of dimensions. So array 2 int says there are 2 dimensions, but the actual size of the dimensions is only known at runtime. So you can't check that at compile time. And dynamic, which has no shape information at all. So array int says, well, it's an array of int. I have no idea what the shape is at compile time. That's all runtime information. And of course, the ones that where you have runtime information about the shape, they do the checks at runtime and they will just throw an error if the shapes don't match properly. So unfortunately, the APIs have to be slightly different, but I've tried to make them as similar as possible. So for instance, the from list, if you have the shaped one, you pass in a type argument that says, I want to make a 3x2 array. In the dynamic one, well, it's a runtime thing. So you pass in an ordinary list that says 3x2. I want to make a 3x2 array. So if you have one of these, a shaped or a dynamic or a ranked, converting between them is very cheap. It's only, well, from stronger type to weaker type, there's nothing to do at all. The other direction, you have to do a little dimension check. So that's one variation. Sadly, there is another variation. So if you want to do efficient manipulation of arrays, you need them to be unboxed. So for instance, the efficient Fortran implementation or whatever of matrix multiply, they need to be unboxed arrays of things. And so there are 4 variations of this library, depending on what kind of boxing you're going to be. So things can be boxed. Then the underlying storage that it uses for the array comes from data.vector, which is a nice efficient vector library for Haskell. Boxed vectors, so all the elements are boxed. They can be unboxed from data.vector unboxed. These 2 libraries have exactly the same API. It's just that there are some constraints. You can't unbox anything. You can only unbox certain things, for instance, numbers. Even more constrained is the one that's called storable, which again has the same API, and it's again unboxed things you have, like unboxed numbers. But now the actual storage is actually pinned in memory, so it is at a fixed address. The garbage collector cannot move it, and that's so that you can call into C code or whatever with this, because you can't have the garbage collector move things around. It has to have a fixed address. And then there is a 4th version of it where you can decide what kind of storage. So it's sort of polymorphic in the storage. You can provide whatever you like. Which means there are 4 versions of this sort of the storage stuff, and there are 3 versions of the type level, which means there are actually 12 different modules you have to pick from that all have kind of the same API, but gives you slightly different things. And it's sad that there has to be 12 things, because the code for them are pretty much the same. Not quite, with the different typing. So I regard this as a sort of flaw of the abstraction power in Haskell, especially this storage one. It should be possible to be polymorphic in your boxedness. And I think these things are coming to Haskell. There's this new thing called levity polymorphism that might be able to do that. Okay, so some words about implementation. What does it look like? Well, so for an array, for each of the dimension, you know what size it has. So if it's a 2x3 array, the sizes are 2 and 3. Then there's something called step, the step size, that tells you if you need to get from one element to the next element, how much do you need to step in this vector? So this vector stores the actual elements. And this tells you to get from one element to the next, how much do I have to move in the vector? And then there's also an initial offset into the vector. And so if you have some indices, you need to index by I1, I2, I3, then you can find that element in this vector by taking the first index times the first size, the step, second index times the second step, and so on. And you add the offset, and that will be the position in the vector. So to show a couple of examples, here is the 1, 2, 3, 4, 5, 6 array again. So sizes are 2 and 3, and the steps, well, if you're on the outermost dimension, the one with size 2, if you want to move from 1 to 4, you need to add 3. So that step is 3. You need to add 3 here in the vector, and the offset is 0. I mean, you could have a bigger thing. So if you take a slice, the offset might not be 0. So for the most strongly typed that have where the size, the shape is part of the type, you don't actually need to store the sizes because they're part of the type, so they are known by the compiler. But for the other ones, the ranked and the dynamic, it's actually part of the storage that you have for your array, that what size the sizes are. Here's a slightly different example. So here's a 3x4 matrix that is full of 7s. Well, you can represent that with a vector that has only a 7 in it and size is 3x4, and it says to get from one element to the next one, you step by 0. Because, well, they're all there. If you don't move around, you get 7 every time. And that's how, sort of, when you do this stretch operation, that it doesn't duplicate any storage. It just sets one of the steps to 0. So it's saying that if you're moving in this time along this dimension, you don't need to move at all. Here is an example of a transpose. So you have 1, 2, 3, 4. It's this array here. What do you do when you transpose it? Just the transpose 1, 0 that we had. You just need to swap the sizes and you swap the steps. Oops, it's not supposed to say offset 1 here. It's supposed to say 0. I'm sorry. So that's wrong. The offset should be 0. No need to move any kind of data around here. You're just saying, yeah, well, for the outermost dimension, you now need to step by 1, because to get from 1 to 2 here, you step by 1. And then the innermost dimension, you need to move by 3, 1 to 4. Too much copy and paste. Here's another example. If you take a slice of an array, so here's a 2x3 matrix. Again, same one. If you take this 2x2 slice that has 2, 3, 5, 6, what you need to do, well, you don't need to do much. You change the size to be the correct one. You leave all the steps alone, and you just change the offset, saying that, well, we start at 2 now. So to get from 2 to 3, it's the innermost dimension, you move by step 1. If you want to get from 2 to 5, well, you move by step 3. So 2, 1, 2, 3, you get to 5. And so they didn't need to touch anything except this stuff here in the thing that's often called a dope vector. So this way of implementing arrays was done in APL also a long time ago, probably 60s, at least early 70s. So that's all I had to say. If you want to try it out, you can download it from Haskell. And there is sort of an accompanying package that has the fast matrix multiply. And once you have matrix multiply, and you can also implement convolutions fairly easily. This second package here also has an implementation of convolutions. If you have matrix multiply and convolutions and all these sort of structural operations, you have basically everything you need to implement neural nets and do some machine learning experiments, which is why I implemented this in the first place. All right, that's all I had, and I see no questions, sadly. I really dislike giving talks this way. It's so much nicer to be able to look people in the face and force someone to have a question.
Yeah, I agree, Lennart. It's much easier to have like a discussion with people when you're face to face.
Yeah.
Could be talk out in the void in a sense.
Yes, it's hard to know if anyone's listening.
Yes, exactly. I have a question.
Yep.
I don't see any questions, so I'll just shoot away my questions. Has this been used in any live application for ML or neural nets?
No.
Or it's been used in
So
experimental ways, or?
so we used it in experimental ways at Google, so to sort of verify some stuff that a compiler we had for a machine learning chip that I was part of developing. Unfortunately, they closed down the project when it was almost done. The pandemic came, and the CFO of Google said, "Oh, we need to save money now because the pandemic is going to be terrible for Google. So let's shut down some projects." So they did that. And then it turned out Google made more money than ever during the pandemic.
It was just the inverse of what the CFO thought.
Yeah.
Yeah. Yes, let's see. No more questions. Are you coding Haskell today, or are you coding C++ at Epic?
No, I'm doing Haskell, but it's, well, we just hired Simon Peyton Jones as well. So we are the only two Haskellers at Epic.
Currently. But soon
Currently.
3, so you 50% growth. Or yes. Did we lose Lennart? Yeah. No.
Well, I think things froze up here. So if you said anything, I missed it.
Oh yeah, we thought we lost you, but you're back. I said, like, if you hire one more, the growth is 50% of Hasklers in Epic.
Yeah. So Tim Sweeney, who still owns the majority of Epic, is very interested in programming languages. He's a programming language nerd. So he gave some talks way back in like 2008 at Popple about some ideal language that he'd like to have. So he's been tinkering with the programming language for the last 20 years.
Oh.
And so, I mean, now he has a lot of money, so now he can afford to hire some programming language people.
Yes, and just try out stuff for fun.
Yeah.
Or for experiment and see where you can go with it.
Well, I mean, there will be some new language for the Unreal Engine in the near future. That's all I can say.
Ooh, cool. We're looking forward to that. Yes. Don't see any more questions. However, a lot of people thanking you for a great presentation. So again, thanks.
Thank you. Thank you for listening.
Yeah, thank you. It's very interesting. It was a long time ago. I mean, I read mathematics in university, I think 15 years ago, and then we did this, like, a lot of array operations. And also,
yeah, I mean, I hadn't done anything like that until I started doing some machine learning stuff. But then you have to brush off all your linear algebra things.
Exactly. Exactly. Yes. Thank you again, Lennart, and thanks for your presentation. Then I'll.
Thank you.
Yeah, you're welcome. Then I'll wrap up the evening. First up, thanks all the presenters, Lennart and Ben, for coming and presenting. Thank you very much, and thanks for all the viewers and watchers. Thank you also very much. We are back on the 15th of February again at 8 o'clock. We have one presenter ready, and we're looking for the next one. So if you want to present, please reach out to me over LinkedIn, Twitter, wherever you want to reach out to me. If you find the contact details either here in YouTube or in the meetup page. Yes, and please remember, if you want to support the community, please remember to subscribe and go over to the meetup community and join us there also. Again, thank you for watching tonight, and have a nice evening, everyone. Bye bye.